Okay, so let's start. Can everyone at the back hear me properly? Yeah, okay, perfect. So we'll switch gears and we'll be moving away from neural language models. We'll be talking about hidden Markov models today. And this is a three-part lecture. So today we're doing session one, and there'll be two more sessions on hidden Markov models. Okay? And the logistics are pretty much the same from last lecture. There is a tutorial for A2 in person. Is the last tutorial with one of the head TAs, Frank. So please attend it. And then we do have office hours on Wednesdays, 12:30 to 1:30 as well. That means today as well. If you please utilize the office hours if you have any questions. And as always, if you have any feedback for me, please feel free to share. Very much appreciated. Okay, so today's lecture will be a little bit interactive with the examples, and I'm hoping that you can help me out as well, as I don't remember the slides, so we can just figure out any numerical problems together. Okay, what is Markov model? A Markov model is a statistical model that assigns probability to a sequence of events. So, for example, here we see 7-word vocabulary: ship, pass, camp, frog, and so on. And then the Markov model can be used to assign a probability when we have a sequence of these vocabularies. And the Markov assumption is that the probability is conditioned on some past window. So it could be just one. If it's one Markov order, then we're just considering the probability of our current word based on the previous one time step or one word. And if it's, so we have seen this in lecture 3 on the n-gram models. And here we can use, the bigram model or the n-gram models are actually instances of Markov decision processor or Markov model. Here we can formulate the sequence ship, pass, ship, and tops as a bigram model. So from your language modeling experience, we know that if we were to model this as a language model, then we do this as our ship given our first start of sequence token, and then ship given the previous word, and so on until we reach tops given the previous word, which is ship, and this would give us the probability of this given sequence. Thanks. Okay, so we can describe the same idea conceptually using a graph. So here we assign each of the tokens in our vocabulary as one specific states. So we have 7 states over here, and then each of the state represents one words that we observe. If we do this, then we can also have discretized time steps. And at each time step, there's exactly one state, and we can corresponding to an observable token. So in this example, in the figure on the right-hand side, we are observing the word ship at time step t equals to 0. And then we have n number of different states, and and we can start from any state. And there's a variable that we use to denote this start initial probability, which will denote by pi. So in this example, the probability of observing ship in the first time step t equals to 0 is given by the initial probability distribution, initial state probability distribution pi, and then ship. Okay, that makes sense? So at each step, we move to another state with a certain probability. We call that the transition probability. So here, the arrows represents this transition probability. So they're color-coded. So for example, the red arrow over here corresponds to the probability of being in state ship and then falling back to the same step. Similarly, the arrow over here with orange denotes being in probability going to the state tops from ship, and so on. Okay? One thing to notice over here is that the probability of frog given ship is 0, And the reason is because if you look at the transition graph, there is no arrow from ship to frog. And thus, we are saying that, like, you know, the probability is 0. And for this to be, yeah.
So the state, like the current time step, the state only depends on the last state.
Right. Yeah. Yeah. And that is because we're making a first order Markov assumption. We're saying it's a bigram model. For this to be a valid probability distribution, we're saying that the sum of all outgoing arcs must sum to 1. Okay, so in this case, if you take the node ship over here, then the sum of the probabilities from ship to ship, ship to pass, and ship to tops equals to 1. So how can we use this graph? So Markov model is a generative statistical model. So if we have a graph like this, and if you say, like, you know, sample randomly, which means sample 500 data points randomly, which means that you'll be just taking 500 steps. If you take 500 steps in this graph, then you'll be generating like 500 tokens, and you have randomly generated sequences, right? And if you have that data, then you can also calculate the likelihood of each of the path, or, you know, each of the state distribution probability. So yeah, so you can use this graph just to randomly walk in this graph, and you can generate sequences. Now, what if these probabilities of whatever we're observing on the surface from actually dependent on an underlying hidden state? What then? Then it would be a multivariate system. So in our running example, we can say that we have 3 different moods, and the moods will be our hidden state. And we'll use this running example where we denote this emoji as being in the disgusted state. And the other 2 are self-explanatory. This is sad, and this is happy. Okay? And each of the states, depending on what is our mood, the probability of observing the words are different. Okay? And we'll call the states as our hidden variables. So over here, we make another, if this variables, like if our hidden states were to change over time, then also, like, our probability of surface words would be different. So here, this emoji graph sort of shows the transition probability between the 3 different states. And based on that transition, you'll be using different, this, what we call emission probability. So the probability of observing a word token given in this state, this is the emission probability of the word ship when we're in this state disgusted, and so on. So we have 3 different emission probability table for each of the different states. Okay, so in the case where we actually had access to our underlying emotional state and all the data were observable at every time step, then this becomes a simple problem. Like, we can calculate the probability of our observation by calculating just a maximum likelihood estimation. So how would we do that? It's pretty much straightforward. It's mathematically formalized in the top equation over here. So let's say you're at time step t, and you have watched the observation from 0 to t, and you know that what are the states, corresponding states in time step 0 to t, and then you want to calculate the observation probability. So that would be basically, like, you know, the probability of this is the state transition, so you're moving from state qi minus 1 to qi, times the probability of, times the emission probability, that is observing the word I when you're in state qi, and do that for all the time steps. Okay, so as a concrete example on the bottom, you can see that if you have 2 time steps and your observations are ship and pass, so in this case, I'll denote, let's say, observation 0 as ship, or first observation, and the second observation at time equals to t equals to 1 as pass. And our states, we have 2 states at time equals to 0. This is our Q0, we're happy. And in the next time step, we are disgusted. Okay? So if we're given this information, Then calculating the observation probability is trivial. We first start with the probability of starting in a happy state, which we called our initial state probability, okay? So this is probability of Q0 times observing the first observation, which is ship, given we're in happy state, okay? Times the probability, the transition probability, because in the next time step we are disgusted, so there has to be a probability of transitioning to the another state, times the probability of observing the second variable at time t equals to 1, given we're in whatever state we're in, okay? So the question is that how do you learn these probabilities? Again, if everything is observed, if we have our observations available and underlying states available, then it's just like maximum likelihood estimation. You can use your training data to calculate these probabilities, no problem. But now here we're interested in the scenario where we don't have access to this hidden state variables, or we don't have access to our underlying emotional state. We are only observing observation in forms of word tokens. And then how can we calculate the probabilities of our observation is one problem that we want to find out. So we see these examples, like you can ask that where, like, you know, this problem surfaces in many different domains, or some concrete examples could be just in natural language processing, you observe sequences of words. But what generates these words, that could be treated as an HMM problem in the sense that we know about parts of speech. We know how we can do dependency parsing on our words, you know, noun, subject, verb agreement, and things like that. So we can say that there's an underlying parts of speeches that generates the words that we see. It could also be like our translation task, where we're observing English phrases, but that are being generated by some hidden French phrases. And it could be extended into other domains, like in cryptography, you're observing encrypted symbols, but those are being generated by some hidden messages. And in finance, like you're observing stock prices as the observable phenomena in the market, but those are the outputs of some hidden market conditions. So let's formalize the notion of hidden Markov model. So we can formalize HMM as this 5 tuples over here. First we have S. S is the set of all states, possible states. In our running example, this is the 3 moods. And then we have W, which is the output alphabet, our observation tokens that we see. And then pi AB represents our model parameters theta. Pi represents the initial state probabilities. A represents the transition probabilities between the states. And the last one, B, represents the state output probabilities. In literature and in most places, it's also known as emission probabilities. So when I say emission probabilities, I'm referring to B. So emission is the probability of emitting observation O. That is the emission probability or state output probability. And then we have our state sequences at the bottom, Q, represented by Q. And we have our observations or output sequence denoted by Omicron or O. Okay, so if we have a formalized notion of HMM, how can we use this for generating sequences? Okay, so let's say we have a process that is HMM process, and we can use the simple algorithm to generate sequences using our HMM model. If we have a model, then you can just say that, like, okay, so we'll start at time equals to 0. We'll start in some state with probability given by our initial state probability. And then we'll just emit symbol O0 with the emission probability, okay? And then I'll continue to do that for a certain number of steps, as long as we want whatever the length of our sequence we want to generate. We just go from one state to the other state in the next time step and emit some observation based on the probability. And we repeat this like n number of or t number of times, and then we have generated sequences of observation going from O0 to, let's say, OT minus 1, okay? So we will be looking at, there's three fundamental tasks that we can solve with hidden Markov models. The first one is computing the observation likelihood. So you're given an HMM trained HMM model, and you see some observation, and you're asking the question that what is the probability of this observation? Then second, we're trying to explain that you see some observation and you have a model theta, but now you're asking that what is the best possible state sequence that generated this observation? So this is the task of inference. And lastly, we have the task of training, which is essentially you have a bunch of observation and you have the model parameters, and then you're trying to fit your model, find the best parameters theta based on the observations. So that's basically the task of training. And then remainder of the lecture, we'll be looking at algorithms and ways to solve these three tasks. So for the first task, we'll be looking at the first two tasks, actually, we'll be looking at dynamic programming methods. So for the first task, we'll be looking at forward-backward procedure in today's lecture. And for the second task, to find the optimal state sequence, we'll be looking at this dynamic programming algorithm called Viterbi algorithm. And for the third one, for the task of training, we'll be using a form of expectation maximization algorithm, specifically Baum-Welch algorithm. So I want you to keep this at the back of your head, that what you're trying to do here. There's three tasks we need to solve. And first today, we're just trying to find out, using forward-backward procedure, how we can find this guy over here, probability of our observation likelihood. And then next lecture, we'll be looking at the Viterbi algorithm, where we'll be focusing on finding the best, the Q star, or the best possible state sequence. And in the third session, we'll be looking at Baum-Welch algorithm, which is a form of EM algorithm. And we'll be trying to find theta, or fit our model theta star, okay? Okay, so let's, okay, so before we move on to task one, let me ask this question. Now, this will not be in your test. It's just, I think it's getting a little bit monotonous, so maybe we can shift gears a little bit and solve this brain teaser. And whoever answers this question gets no, I mean, nothing, just my appreciation. But yeah, so who can answer this question? Yes.
4.
4? How?
4 5.
4 5s. Okay, is that the minimum? That's one solution, actually. I give the answer. Okay, no, anyway, so yeah, the answer is 2 if you can. It's, yeah, anyway, yeah, that's the right answer if it's just in one dimension. Okay, anyway, let's go back to the main course materials here. So yeah, so we need to solve 3 tasks, and right now we're focusing on the first task of computing our observation likelihood. So our observation likelihood is the joint probability of the observations and the states, and that can be broken down. This is the mathematical form. And if we use the HMM formulations that we looked at a couple of slides back, then we can denote this using those formulations. So initially, we start off with our initial state probability at Q0. And then you'll see this pattern that, okay, so then you have this emission probability. Okay, so you're emitting observation T using the emission probability. And then you have the state transition probability at every time step, because you could be transitioning to another state. And then again, the emission probability of emitting observation T in that state, okay? And then this sort of repeats. So if we want to get the probability of our observations without seeing the state, we have to sum over all possible state sequences, okay? And as you can imagine that if we try to do that, it will lead us to infeasible computation scenario. And that's exactly what happens, that if you consider each observation of length t, then each state sequence involves 2t multiplications coming from, like, the state transition observation and start state. And then we have n to the power t possible state sequences for every time step, right? So if you have n possible states at every time step and you have length of t, then it becomes infeasible because we have to do this, like we have to O n to the power t possible multiplications, and that makes this infeasible. But this is the naive way if we do this, but obviously we're not going to do it in the naive way. So we will be using dynamic programming for solving this problem. Because as you have seen that there's substructures that are repeating, so we can always, like, compute those substructures, subproblems, and we can cache it. And then we can just use those values to recompute. So this is perfectly set up for applying dynamic programming. And in order to do that, we'll be looking at 2D matrix or trellis with our states and time, okay? And each element at IT, so remember that we'll be using phi IT, where phi IT means the probability of being in state I at time t, after seeing all the observations up until that point, okay? So we've seen all the observation, we are in state I, or SI, and this is the probability, okay? So how we can use this? Let's take a look at this. So this is our trellis structure. The x-axis shows the time. It's 0 index, so we go up until t minus 1, and we have n number of states, okay? And we'll go left to right in this computation. We'll go left to right because the natural flow of time, and top to bottom just we can, because we can, it doesn't really matter. And so first we will look at the procedure, forward procedure, where we're going left to right. And then after forward procedure, we'll do exactly identical thing, but we'll be doing from back to front. And then we'll look at that, what happens if you combine forward and backward procedure, okay? But if you understand forward procedure, backward procedure is the exact opposite thing, but we're starting from right, coming to the left. Okay, so what does the arcs represent? So we should understand that these arcs over here, for example, the first one, the top orange one, this represents the transition probability. So at time equals to 0, we're in state 1, and this arc gets us to state 2, right? So there's a transition probability, S1, transition probability of going from state 1 to state 2, times what we observe at time equals to 1, which is our emission probability being in state 2 of observation 1, okay? And if you understand that, then all the arcs or arrows are, like, they represent the same thing. So the transition probability times the emission probability in whichever state you're going to, right? So the same thing at the bottom red one, it's basically first the transition probability from going to state N to S3, and then times the emission probability of observing O2 from state 3. Okay? And we obviously can reach yellow from many different paths. Yellow, this orange is one such path, but we can also come here from this purple path, or we can also come here from this red path, right? And but one thing we can notice that if we're passing through this green path over here, that we have already calculated the value or the probability of passing through this path before. So it sets up for us to apply dynamic programming, so we can use the previously computed value in order to do our calculation for the orange, yellow node over here, okay? So yeah, So basically, yeah, so you could be, so if we know this value over here, that captures all the possible paths that's coming from the previous time step. Pretty basic dynamic programming stuff. And then here, yeah. So this guy over here is basically capturing this arrow over here. You're going from S2 to S3 and the emission probability of observation 2. So in order to calculate, what is phi 21, which node? Which node is phi 21 here? Yeah, so this guy, right? So this captures all these probabilities, right? So at every, like we can just calculate phi by doing like, a summation over all the possible states of the previous phi values in the previous time step, and so on. Okay. So yeah, so in order to compute the probabilities of the black node and the yellow node, I need, among other things, the probabilities of the orange node and the purple node, like this guy's here and this guy's here. So I guess you're already getting the idea that we'll just like calculate the value for each of these nodes. We're going to cache it, and when we calculate black, we're just simply reusing this value. So that's the basic idea. So the forward procedure, phi it, is the probability of all the probability of a node at state I time t. That is the probability of all the observation tokens you have seen until time t, and given that we're in state Si, okay? And we already have the value from the previous states Sj, like in the previous time step, and we use that knowledge, plus our state transition probability from going from those previous states, coming to our current state, and the emission probability of, emission probability of observation t from our state, okay? And we compute the trellis left to right and top to bottom. Note that observation is fixed and known, and phi, the expression phi it, or the function phi it, is agnostic of the future, okay? All right, so the forward procedure has 3 key steps. First is initialization, and then induction. So in the initialization process, we just compute the first column of the trellis using our initial state probabilities. And in the induction step, we iteratively compute all the nodes in the rest of the trellis based on our previous values of phi it. And in the conclusion, to get our answer, we essentially sum over all the nodes in the final column, which is t minus 1. At the last time step, we just calculate sum over all the nodes in the last column. So let's see an example. The initialization procedure. So first, we're calculating the yellow node over here. So we know we'll be using the initial state probability pi I and the emission probability of observation 0 over here. And we repeat that for all the steps. So this first column is initialized. And then we have the induction procedure. And in the induction procedure, we'll be using all the values that we calculated in the previous state. So, and basically phi it for this yellow node over here. And then for each of the states, we're calculating the state transition probability. And then finally, just multiplying that with our emission probability of our observation at that time step. Okay? And we do this until the penultimate time step, which is t minus 2. And then we apply the conclusion procedure. Okay, so any question? This is another pictorial depiction of of the induction process for one single node denoted in yellow. So you're in state Sj, and then we're calculating phi jt plus 1 from all the previous phi values in the previous time step. Okay, so now that we have applied the inductive step, now we can do the conclusion step by summing over all the possible states in the very last column over here. And we simply go and sum up all the phi values for t minus 1. There is no transition probability or emission probability because we're in the last time step. Okay. All right, so let's take a quick example of the forward procedure. So here, first we want to, so our observation, it's 3 time steps. We have 3 observation tokens, mother, frog, and ship in sequence. And we have the 3 states, the mood states. And then we're trying to calculate our observation likelihood. Okay. And first, we need to apply the initialization procedure, which is basically filling out the first column. And we do that how? So what will be this value over here? Our probability of starting in the disgusted state is 0.80. And what else do we need? So pi 0 times the emission probability, right? So the probability of observing mother in the first time step. And I think the emission probabilities were given in the earlier slides. But essentially on the figure over here on the right hand side, you have the state transition probabilities and you have the initial state probabilities. And this will be the emission probability. It's an observation of the probability of observing mother in the first time step, okay? So it's 0.08 because the 0.10 is our emission probability. Okay, why is this 0 for happy? Yeah, so the initial probability of starting in happy state is 0. That's why this is 0. Okay, so we have done the initialization. So next we will be doing the inductive step. And the induction step is for frog, for this node over here, we use all the previous phi I values that we just did for initialization. And can someone explain to me what are these numbers here? So 0.08, I see that it's coming from phi IT. And this is what? Right, the transition probability. And this one is the probability of observing what token? Frog in state. Okay, yeah. And so we do this for all the 3 states. So 0 means what? That the transition probability must be 0, right? The transition probability to state disgusted from happy should be 0. That's why this guy is 0 over here, right? Is that the case? Yeah. Yeah, so if we're in a sad state, then we can't move out of that. So transition probability is 0. Okay, makes sense. All right, is this clear to everyone? Cool. All right, so we're done with the induction step, and in the conclusion step, we will just be summing over the last column over here. And that gives us our answer, our observation likelihood. And we're done. Okay. All right, so what does the forward procedure, so what does the forward procedure give us? That we basically improved our computation time from the naive approach, which was O n to the power t. We're using dynamic programming, and now it's quadratic number of multiplications. It's more feasible, and ultimately it gives us the observation likelihood. And now remember that we could have done the same thing from back to forward, and we call it the backward procedure, which we'll be looking at next. So I actually, so we can ignore this 2 slides. So again, a reminder that the whole point was to find out the observation likelihood. So we're still in the space of task 1. We're still in task 1. We're trying to calculate the observation likelihood. And we know from our forward procedure, we know that like what phi looks like, which is depicted over here. So it's basically like, forward algorithm stores all possible 1-state sequences from the start to store all possible 2-state sequences from the start to store all possible 3-sequence states from the start. So just like that, right? And for the backward procedure, we do this exact same thing, but we do it, we're still calculating the observation likelihood, but we're starting from the right and then we're going forward, okay? And yeah, so we're storing, yeah, go ahead.
Does using the trellis method significantly increase the memory we need to store compared to the naive method?
How? The naive method, you know, I mean,
we need to store the
so in the naive method, you are, I mean, yeah. So when you're doing dynamic or like any kinds of recursive calculations, there will be like you're storing those intermediary values. But then if you're using the naive method, then there's n to the power t possibilities, right?
Which, yeah, you're saying if the state, there's a lot of state and a lot of time steps, wouldn't that,
right,
you know, exponentially?
It is, but there isn't any better way to do it, right? Like, yeah. Yeah, so yeah, it's a good question. So in the backward pass, we also have that initialization step and the induction step. So maybe I'll just quickly go to the punchline and then we'll start with the backward procedure next lecture. So initially, the initialization, we start off the right, we assign a value of 1 and then we go from there, okay? So the main idea of the backward procedure is like we use this variable beta. So we have seen alpha before. And now we're saying beta it is the probability of starting in state I at time t when you have observed everything in the future that comes thereafter, right? So the trellis is computing right to left. So now you see it's falling into place. So with phi I, we've seen like left to right. And then with beta I, we say right to left. So if we combine these two approaches, so backward procedure also has 3 steps. The initialization step where we assign 1 to the final column, and then we go backwards. And you sum over the possible states. I'll review this at the start of next class, but the main idea is that if you combine alpha and beta, so far, yeah, so far like with the alpha forward procedure, you're calculating your observation likelihood over here, like you have to go to t minus 1. And with beta, you can calculate the observation likelihood at like the reverse process equals to 0. But if you combine alpha and beta, then you can just use any time step and you can just use alpha it times beta it, and then you have the observation likelihood, okay? So that gives us, that is the main advantage of like combining the alpha I and beta I, and we can use this in solving future tasks as well, other tasks that we'll see. But yeah. And one thing to notice is that alpha it incorporates all the probabilities of this time step, and beta it calculates all the probabilities like in the future time steps. So from here to here, it does not incorporate like time t itself because alpha it is capturing that probability. But yeah, with that notion, I think that is the main idea. So we'll start off with backward procedure, quickly review it, and then we'll go on to the second task, which is Viterbi algorithm, and then Baum-Welch for the next 2 lectures. Okay? All right, that's it for today's lecture. Thank you.